You know, it's really funny how easy it is to look at the physical world around us, right?
Oh, yeah, for sure.
Like you see a satellite maintaining orbit, or just the smartphone in your hand,
Mm.
or even the software architecture managing a massive power grid. And we just completely ignore the invisible scaffolding holding all of it together.
Right, because you just naturally assume that scaffolding is made of, titanium or silicon.
Exactly. Or like millions of lines of code.
Yeah.
But if you strip it all the way down, I mean, all the way down, the actual foundation for those complex systems isn't a material at all. It's calculus.
Which is wild to think about.
Right. And today, on the deep dive, we are going to look specifically at how engineers use advanced integration techniques to literally design reality.
I love this topic because it fundamentally changes how you view engineering. We're looking at operations that most people, well, they just write them off as abstract academic
Like
exercises.
stuff you just leave on a chalkboard in college.
Exactly. Specifically, we're talking about integrating complex rational functions using partial fractions and integration by parts. But instead of leaving them on that whiteboard, we're going to translate those exact mathematical operations into the actual physical and digital architecture of our world.
We're basically taking off the mathematical blinders for you today. So
Duo.
let's start with the first major hurdle that engineers face, which is dealing with coupled systems.
Yeah, the coupled systems they're tough.
When we look at mathematical modeling, you frequently encounter what's known as a complex rational function. So you've got a polynomial divided by another polynomial, usually written out in textbooks as like p of x over q of x.
Right, and in physical engineering, that fraction basically represents pure chaos.
Chaos.
Well,
Really?
absolutely. When you have variables stacked in the numerator and this dense polynomial in the denominator, you are looking at a literal mathematical knot. The forces or the signals you're analyzing, they are deeply entangled. You can't integrate that function directly because the physical phenomena it represents are just interacting nonlinearly. It's a mess.
Okay, let's unpack this. So to integrate it, you have to use partial fraction decomposition. As long as you have what they call a proper fraction, meaning the degree of the numerator is strictly less than the denominator, you can basically reverse engineer it.
Yes, exactly.
You take that messy denominator, say it's a coupled system represented as 1 over the quantity x minus a times x minus b, and you mathematically force it apart into two separate, simpler fractions.
Right, so you get a over x minus a plus b over x minus b.
Right, which is an incredibly powerful algebraic maneuver. But why would an engineer ever need to unbake a mathematical cake in the real world? Like, what is the actual point?
Well, by isolating those components, you bypass that impossible chain rule problem. Those distinct separate fractions now integrate trivially into basic logarithm functions. So you've taken this monolithic, totally unsolvable system and fractured it into manageable pieces.
Right, and to visualize this, because unbaking a cake into flour and eggs is physically impossible, I think of it more like um, running a beam of chaotic white-hot light through a spectrometer.
Oh, I like that.
Right. You are mathematically refracting that really dense beam into distinct measurable wavelengths, your reds, your greens, your blues. So you can measure the energy of one specific wavelength completely independent of the others.
I vastly prefer that analogy. It actually reflects the precision of the math. We aren't doing parlor tricks here. We are isolating specific frequencies or forces from a highly noisy environment. And the physical world, it rarely hands you clean, isolated variables.
No, not at all.
Real-world physics is exactly that, a massive, noisy beam of white light.
Which brings us to a highly practical application from the source material today, aerospace engineering. Specifically, looking at the central bus structure of a satellite.
Right, the bulkhead.
Yeah. When you are designing that main structural framework, the total mechanical stress acting on that titanium is a highly coupled rational function.
It's an absolute nightmare of intersecting vectors. I mean, you have severe thermal loads from solar radiation hitting one side of the spacecraft, right? Causing rapid material expansion.
Right, it gets super hot.
Exactly. But simultaneously, you have violent acoustic vibrations from the rocket engines during launch.
Oh, wow.
And on top of all that, massive axial g-forces pressing down. They are all happening concurrently. They interact with each other in one giant coupled equation.
And this is where the theory hits a very hard wall of physical reality.
Mm.
Because I was reading the source, and one quote really stuck out to me. Wait, you literally cannot design a bracket to withstand a coupled equation.
No, you really can't, because a physical piece of titanium doesn't have an average response to heat, sound, and gravity.
Right.
Thermal expansion requires a certain type of material flexibility or maybe shielding, whereas acoustic vibration requires dampening, and axial G-forces require rigid, high-tensile reinforcement.
Those are completely contradictory material properties.
Yeah.
Exactly. If you try to reinforce the metal for the overall average stress of that massive polynomial fraction, the bracket will fail. It will snap from the vibration or shear from the thermal expansion just because you didn't address the specific vectors.
So the engineers apply partial fractions.
Yes.
They take that single chaotic aerodynamic load, the P of x over Q of x we talked about, and they mathematically decompose it into distinct point loads.
Yes. They refract the light, to use your analogy. Suddenly you have one piece of the equation, let's call it A, that represents the thermal load in total isolation, and another piece, B, representing only the acoustic vibration.
That is so cool.
It is, because now the structural engineer can design a composite material where, say, the outer layer is optimized entirely for thermal expansion based on equation A, while the internal lattice structure is tuned specifically to dampen the acoustic resonance of equation B.
Wow. They literally use calculus to digitally separate physical forces so they can build hardware that survives space.
Exactly. It's essentially computational triage.
Computational triage, I love that. But this isolation technique isn't just limited to giant mechanical stresses, right? It scales all the way down to the microscopic level too, like in control systems and signal processing.
Oh, yeah. If we connect this to the bigger picture of electronics, engineers rely heavily on Laplace transforms to understand how circuits react to inputs over time.
Right, like the audio equipment you listening to this deep dive are using right now.
Yep. Which utilizes RLC circuits, resistors, inductors, and capacitors all working together to filter signals.
And when you mathematically model an RLC circuit, you run into that exact same entanglement problem.
Even worse, actually. Differential equations in the time domain are notoriously brutal to solve. So electrical engineers use the Laplace transform to shift the whole problem out of the time domain and into what they call the S domain.
The complex frequency domain.
Right. It basically turns agonizing calculus into somewhat simpler algebra. But, and this is the kicker, the output, the transfer function, is a massive, ugly polynomial fraction in the S domain.
So it's the exact same entangled mess as the satellite bulkhead, just mapped in electrical frequencies instead of physical gravity.
Precisely. So what do? They apply partial fraction decomposition. The electronics engineer breaks that massive transfer function down into individual time constants.
Okay, right.
They extract an isolated RC resistor capacitor time constant and an isolated RL resistor inductor time constant. They take the complex electrical behavior, isolate the fundamental building blocks, and then they can tune the circuit's filters perfectly.
Okay, so that makes partial fractions the ultimate mathematical demultiplexer.
Yeah, that's a good way to put it.
But I do see a glaring limitation here. Partial fractions are brilliant when you are dealing with rational functions, polynomials that can be neatly factored and pulled apart algebraically. But what happens when your physical system introduces something that isn't a polynomial? Like, say, an exponential decay rate or a sinusoidal wave. The pieces just don't fit together neatly anymore.
And that is exactly where partial fractions hit a brick wall. If you are trying to integrate a function where a simple algebraic variable is multiplied by a transcendental function, like x multiplied by e to the power of x, you can't just decompose it.
Because they don't share a clean chain rule relationship?
Exactly. They are fundamentally different mathematical beasts.
So we need a different structural blueprint. Which brings us to the second big concept, integration by parts.
Right. So integration by parts is basically the inverse operation of the product rule from differential calculus. The product rule tells us how to find the derivative of two multiplied functions. By reversing that logic, we get the integration by parts formula.
Which is the integral of u dv equals u times v minus the integral of v do.
That's the one.
Now, I know that formula can sound a bit like alphabet soup when spoken out loud.
Mm.
What is the actual mechanism at play here? How does swapping u's and v's solve a system that refuses to be decomposed?
Well, it's a mechanism of strategic reduction. You have this messy product of two functions. You assign one part of that system to be u and the other part to be dv. The whole goal is to choose u so that when you take its derivative, it gets structurally simpler.
Right.
Meanwhile, the dv portion must be something you can easily integrate without it exploding in complexity.
But you don't just guess at that, right? Like, if you pick the wrong u, couldn't that second half of the formula, the integral of v do, end up being vastly more complicated than the problem you started with?
Oh, it absolutely can. And that is a classic trap in signal analysis. If you assign the variables backward, your equation just balloons out of control. To prevent that, engineers use a strict heuristic for choosing u.
The ILATE rule. ILATE?
Yes, ILATE. Inverse trigonometric, logarithmic, algebraic, trigonometric, exponential. You scan your equation, and whichever function type appears highest on that list, you designate it as u.
Okay, so why does that specific order work?
It works because logarithmic and inverse trig functions are really difficult to integrate, but they simplify beautifully when differentiated.
Ah, I see.
And conversely, exponential functions at the very end of the list are virtually immune to differentiation. They just repeat themselves. So you assign them to dv, where their repetitive nature is harmless.
So what does this all mean conceptually? Because it sounds a lot like mathematical judo.
Judo.
Yeah,
Yeah.
you got this heavy, complex problem charging at you. And instead of trying to meet it head on with brute force, you use its own momentum against it.
Oh, I see where you're going.
You strategically throw the complex algebraic part, the u, to the ground, making it smaller and weaker by differentiating it down to zero. Meanwhile, you deal with the cyclical, predictable part, the exponential dv, by just letting it integrate endlessly, absorbing the energy without letting it destabilize the system.
That is a phenomenal way to visualize it, seriously. You are redirecting the energy of the equation to systematically weaken it. And that process of systematic, step-by-step weakening is exactly why integration by parts is the conceptual engine behind modern computational algorithms.
Right, because we've seen how this works for a human on a whiteboard. But how does this actually translate into software architecture?
This raises a huge question about computational load. Integration by parts is actually the mathematical mirror of recursive algorithms, or dynamic programming in computer science.
Recursion, meaning a software function that calls itself to solve smaller instances of the exact same problem.
Exactly. When a CPU is handed a massive coupled computing problem, which is mathematically equivalent to our starting integral of u dv, it is often far too memory intensive to compute simultaneously.
Right, it would just choke.
Yeah, if the system tried to swallow the problem whole, you'd get a stack overflow. The system just crashes.
So the software uses the integration by parts logic.
Yes. It tells the CPU to strip off one solvable chunk of the problem, the u times v part of our formula. It caches that solved piece in memory. Then, it takes the slightly less complex remainder, the integral of v to dua, and passes it back into the function recursively.
It throws the opponent down one level and then assesses the remaining threat.
Exactly. It repeats that exact stripping away process over and over, reducing the algebraic u component degree by degree until the entire massive problem resolves all the way down to zero.
Wow.
It prevents system crashes by turning an insurmountable block of processing into this digestible, recursive loop.
That is beautifully elegant. And it actually ties right back to the electronics example we discussed a minute ago.
It does, yeah. It closes the loop entirely. We talked about using partial fractions to isolate the RC and RL time constants in the S domain, but an engineer can't physically see the S domain.
Right, it's just abstract math at that point.
Exactly. To translate those abstract frequencies back into the real world, to see them as actual voltage spikes and decay curves on an oscilloscope, you have to run an inverse Laplace transform.
Let me guess. The engine running under the hood of the inverse Laplace transform is integration by parts.
You got it. It is the exact mathematical mechanism that pushes the frequency data back into the time domain, allowing the engineer to visually confirm that the circuit won't, blow out a speaker or fry a motherboard.
It really is all interconnected. The partial fractions act as the demultiplexer to break the physical problem apart, and the integration by parts acts as the recursive engine to process it back into physical reality.
Beautifully summarized.
But here's where it gets really interesting. Because in modern engineering environments, no one is actually sitting at a desk grinding out a 5-page integration by parts derivation by hand, right?
Oh, no, absolutely not. That would be a massive waste of human capital. Modern engineering relies entirely on computational software like Python, specifically using symbolic mathematics libraries like SymPy.
Right. So instead of manually factoring the polynomial, isolating the a and b constants, and running the recursive integration loops, A modern engineer can just use SIMPY's optimized apart function.
Yes, the apart function is incredible.
You feed it a chaotic, entangled expression, and with a single line of code, the script computationally decomposes it and sweeps it with an integral in literally milliseconds.
It executes the exact theoretical constraints we've been discussing perfectly with zero algebraic friction.
But I do want to push back on this a little bit because it creates a bit of a paradox, doesn't it?
How so?
If we can computationally decompose and integrate these massive aerospace and electrical expressions with one single line of Python, why do engineers still spend semesters in university learning the manual decomposition? Like, if SIMPY does the heavy lifting in milliseconds, is there any actual value left in the manual technique, or is that just like academic hazing at this point?
It's funny you ask that because what's fascinating here is that this is currently one of the most fiercely debated topics in engineering education right now.
Really?
Oh, yeah. But the consensus remains clear. Abstracting the math away completely leads to catastrophic engineering failures.
But wait, how so? If the code doesn't make algebraic errors, shouldn't it be safer?
Because the Python script has no physical context. A computer running the function executes the logic flawlessly, sure, but the computer doesn't know what it is separating.
Oh, I see.
It doesn't know that variable A represents the thermal radiation of the sun on a satellite, and variable B is the acoustic vibration of a rocket engine. The code just sees integers and variables.
Right, it totally lacks the physical intuition.
Exactly. The human engineer has to know why those forces are being separated, and more importantly, what to actually do with the physical titanium once the computer spits out the decomposed values.
That makes total sense.
If you don't understand the conceptual core, like the manual reality of how those forces were mathematically coupled in the first place, you won't know how to interpret the code's output. Worse, you won't realize when a sensor error causes the code to hand you a physically impossible answer. If you blindly trust the black box without understanding the calculus inside it, you end up designing a bridge that collapses under its own resonant frequency. The math is just a tool, right? The structural understanding is the engineering.
The code is the hammer, but you still have to understand the blueprints to actually build the house.
Perfect way to frame it.
That frames it perfectly. So, to bring this all together for you listening, today we looked past the abstract symbols of calculus and explored the hidden scaffolding of the physical world. We saw how partial fraction decomposition serves as a sort of mathematical spectrometer, untangling complex coupled problems so aerospace engineers can isolate thermal loads from acoustic vibrations, and electrical engineers can tune complex circuits.
And we explored how integration by parts operates as the inverse of the product rule, utilizing that isolate heuristic to strategically weaken systems that refuse to fit together algebraically.
It really isn't just a trick to pass a calculus exam.
No, it is the underlying logic for recursive algorithms in software architecture. And it powers the signal processing that allows us to safely translate frequency data back into the real world.
Understanding these concepts, even if you never manually calculate an integral again in your entire life, it fundamentally shifts how you view reality. It gives you a kind of structural X-ray vision.
It really does.
When you look at the incredibly complex coupled systems of the modern world, from orbital rocketry to massive digital networks, you aren't just seeing magic anymore. You are seeing the deliberate mathematical isolation of variables designed to prevent the system from shaking itself apart.
It highlights the fact that complexity is often just a series of simple systems layered on top of each other, waiting to be properly decomposed.
And that leaves us with one final, slightly provocative thought for you to mull over as you step back out into the world.
Okay, let's hear it.
We've seen that the fundamental secret to solving massive, chaotic physical problems, like launching a satellite without it shattering, is to use mathematical partial fractions to decompose the chaos into isolated, solvable point loads.
Right.
If that structural philosophy works for titanium bulkheads and electrical grids, what highly complex, deeply entangled problems in our daily lives, or even in modern society, might become instantly solvable if we could just find the mathematical courage to decompose them into isolated variables instead of trying to solve all the chaos at once.
Oh, wow. That is a phenomenal question to end on.
Sometimes the most complex knots really just need the right demultiplexer. Keep unpacking the world around you, and we'll catch you on the next deep dive.